Welcome back. So today we are going to start talking about geometric optics. And I want to begin this by doing a little bit of just introduction to things. So let's get that going. All right, so here's the things that we're going to cover today. So talk about reflection. So light waves can bounce off of a surface. We'll talk about rays of light. Rays of light are things that are emitted by laser pointers. That's the model that we will be using for this chapter. So they reflect from the water, form an upside down image of the bird's head. So we're going to learn how the law of refraction can be used to understand how mirrors work. The next thing that we're going to talk about is refraction, which is that as light passes from air into water, from one medium to another, that light actually bends. And so you see here, we see kind of multiple images of what the turtle looks like. So we'll talk about how that works, and we'll get quantitative with Snell's law to learn how to predict that. Once we've got some things about how mirrors work and some things about how light bends as it passes through one medium to another, we'll talk about how light bends as it passes from air through to glass to make a lens. So this is how our eyes work. This is how our eyeglasses work. This is how any number of things work in the world. So we will learn how to calculate these images and characterize what they look like and where they're located using some problem-solving methods for this job. Okay, so we have three models of light. Okay, so we just covered light is kind of this crazy thing, right? So we talked about how we just covered the fact that electromagnetic waves are actually light. Okay, so we're going to cover that next in more depth, or at least some depth as we near the end of the semester, which is that light behaves like a wave. Okay, so that's sort of the next chapter. We also just talked about the photon model of light, which says that light arrives in these discrete little packets of energy called photons. So this is not a wave, this is a particle, right? Light is like tennis balls hitting up against the wall. There's just, billions of them that hit you every second. And right now we're going to talk about a third model, which is the ray model, which is probably the least technically correct way to view light, but it's a really useful way to think about light, to make predictions about the macro scale of things that we observe. So we observe a lot of properties that fall from the ray model of light. So we're going to spend this whole chapter talking about that. Okay, so sources of light. Okay, so sources of light rays. So I have a laser pointer right here. Let me use this one. It's on. Can you tell? I can tell. I can tell because I look up at the ceiling and I see it. If I put this back here, now you can tell that it's on. But the crazy thing about this is that, I know that it's on because I can see that it hits against the wall. But I have no way, I only see rays of light that actually enter my eye, okay? So this laser pointer is shooting out a ray of light, but because none of those rays actually are entering my eye, I can't perceive that it's on. So what goes on against the wall is that when this laser pointer hits the wall, now all of a sudden all those rays of light are scattered around on that bumpy surface of the wall. It doesn't seem bumpy, it seems pretty smooth, but compared to, say, a mirror, it's a pretty bumpy surface. And so now all those rays of light are scattered around, and some of those rays of light actually enter my eyeball, and that's why I can see it. But it's there, and just to prove to you that it's there, when I turn this on, I have some chalk dust here, hopefully. So I'm kind of dusting this laser with chalk dust, and now you can see what's going on, that the laser pointer is on. So what goes on when the chalk hits the laser pointer is that now I've given the light something to scatter off of. And so once the light starts to scatter, the rays of light scatter in all directions, some of which enter my eye and I can see them. Okay, so we're going to think about this as being the ray model of light. Okay, so what about light bulb, right? So how does a light bulb work? So here's my light bulb, and I can turn it on. And electrocute myself just a smidge. This is, I guess, yeah. Whoops! I just connected myself in parallel with the light bulb, and now it's not on anymore. See if I killed it. I'm not personally dead either. Okay, so this light bulb is on. So how do I know that the light bulb is on? Well, I can think about this light bulb as emitting rays of light equally out in all directions. Okay, and so I can make a shadow on the wall with this light because this light bulb emits stuff out equally in all directions. Go ahead and turn that off and be much more careful with how I touch that in the future. Okay. All right, so there we go. So your eye has a little lens inside of it. And we haven't talked about lenses yet, but I think we're all pretty familiar with the fact that lenses help us focus things differently. So we have a diverging packet of rays that leaves the top of this tree, and our eye takes diverging packets of rays and converges them into a spot on a screen, which we call our retina, in the back of our eyes. Okay? So let's talk about reflection. So how does reflection work? The law of refraction says that the angle of reflection will equal the angle of incidence. And I need to go turn a light off so I can show you the demo about this. Okay. So I have a ray box. So it's shooting out a ray of light, and we'll use this a lot in this class. I can change the settings on it so that it shoots out multiple rays or so that it shoots out a fat ray. But right now, I want one skinny little ray. And I have also a little mirror. And when I put the mirror in the path of this, you can see that this comes out like that. So let's define what I mean. So you can see that like the way that it goes. Let's draw a diagram about what's going on here. So the incoming ray of light goes like that, and the outgoing ray of light comes out like that. And I'm going to go ahead and draw the surface of the mirror like this. And now let's pull it out and see what we can see. I want to keep the lights off for a minute. I think you can still kind of see this. Okay, so we need to draw a normal line. So this is a line that comes out that is perpendicular to the surface. Okay, so we got our normal line, and let's give it, let it auto do itself a little bit better. Okay, well, that's not better. There we go. Okay, so this was the angle of, this is what the plane of the mirror was at. And this angle right here, which is the angle that we measure relative to a normal line. So this dashed line is perpendicular out from the surface of the mirror, is the angle of incidence. And this angle right here is the angle of reflection. And it will always be true for any mirror, no matter how complicated it is, that the angle of incidence equals the angle of reflection. So let me show you a couple of ways that we can convince ourselves that that must be true with this ray box. So, right, with this flat mirror, you can see that happening. I can even use a curved mirror. So here's a curved mirror. And now when I put it in the path, it goes like that. But if I can just try to get this to line up exactly like that, and exactly like that, there you can see it. So this this line that I drew that was a flat surface for my flat mirror is actually a line that is tangent right now. It's a line that's tangent to the curvature of the mirror. But yet again, my angle of incidence equals my angle of reflection. Okay, so I can make that angle bigger. If I make the angle of incidence bigger, I make the angle smaller. If I make the angle of incidence smaller, I can even flip my mirror around this way. And there we go. It does the same thing. Okay. So let's get the lights back on. And so here was our law of reflection, which said that the angle of incidence, which we always measure normal to the surface, equals the angle of reflection right here. So this line here is the normal, and there's the incoming light ray and the outgoing light ray. And so how does a mirror work? Somewhere over here I have a mirror. Here's a mirror, right? That's what my computer screen looks like. How does a mirror work? So let's talk about how this mirror works, okay? Ooh, I even have like a picture and a picture and a picture, which is pretty cool. Right, so the mirror is a perfectly flat surface, or at least very close to perfectly flat surface. So we have these incoming rays of light, and they are all bent such that the angle of incidence equals the angle of reflection. And so if my eye is here, then I will see this packet of rays, and they will enter my eyeball, and I'll be able to focus them. But if my eye is here, I don't see that light, okay? This is what happened when the laser pointer was on, right? The laser pointer is on, but how do you know that it's on? You can't know that it's on unless you have a way to have your eyeball intersect that. And of course, for a laser pointer, you don't want to have your eyeball intersect that light because that would hurt your eyes. But on a bumpy surface, and this is why we were allowed to see it, why we could see it when I hit the wall, right? It's a little bit bumpy, which means that all of these little packets of light individually do follow the law of reflection, right? The angle of incidence matches the angle of reflection, but this surface is just bumpy enough that now, no matter where your eye is, you get to see it. Okay, so when you look into a mirror, you are seeing an image, and that image is a virtual image of yourself, and you're seeing something that appears to be behind the mirror. So let's draw what happens to diverging packets of rays, one packet coming out of here, which we'll call point P, and one point coming out of here, which we'll call point Q. This figure is a little too big, so I'm going to have to draw it on a piece of paper like this. So here is my candle. It looks like that. I forgot to mention in the beginning of this video, but for this video, you need a few things. You need a straight edge. And also, it will be helpful, you can go find yourself a spoon. So pause it and go find those things. But for right now, I just need my straight edge. And if you don't have a straight edge, fold a piece of paper, make yourself a straight edge, right? Fold this piece of paper in half, now you've got a straight line. You just need to be able to draw a straight line. Okay. For later times, I want you to actually have a ruler. And I've got up online, or at least I will very soon before you can see this video. If you don't have a ruler, something that you can print off that will give you a ruler, because it's important that we are able to measure things to scale. Okay, so I'm going to go ahead and draw rays of light. And here's the location of my mirror. I'll kind of draw it like that to make it clear, right? Okay, so here's my point P. And let's imagine what goes on 2 packets of light. So as we said, like this is a point, and it emits rays out equally in all directions. And this is a pretty complicated object, right? So this point is emitting light out equally in all directions. This point down here is also emitting light out equally in all directions. And this point here, and this point here, and this point here, it's a pretty complicated object. So there's tons of different points here that are all emitting light out equally in all directions. So I'm going to draw a few of them as being ones that just kind of come down here. So let's pick 3 of them. I don't want them to be too separate, but I'm just kind of pick a few that are going that way. So these are all 3 rays of light that leave the tip of the candle and go and hit that. Okay, and so I know that they will be reflected. So I'm going to measure out that the angle of incidence equals the angle of reflection. I'm going to try to be careful with this. So here's my normal. And that means that if this is my angle of incidence, and there's my angle of reflection, and this ray comes out like that. Okay. So we'll keep this. I'm going to make this just a little bit bigger. It seems like it's a little too shallow. The first line is the most important. What I was saying is it didn't quite look like this angle and that angle matched, so I'm going to make it just a little bit bigger. And if your eyeball is right here, you see that angle, that ray of light. So it has actually kind of entered my eye, and I see it. But my eye doesn't think that this ray of light is coming from here. My eye thinks that this ray of light has come from a spot back behind that way. So as far as my eye is concerned, right, this ray of light has come in a straight line like this all the way through. Okay, I'm going to do that for these other 2. So I'll put in my normal. That one. Now let's put in another normal. Match it so that the angle of incidence matches the angle of refraction. And there we go. So if I trace all of these back, I can actually see that all 3 of these rays that are actually exiting the mirror to an observer over here, it seems like they come from back here. I want you to look at this. I mean, I haven't drawn it perfectly, but this distance here looks the same as that distance here. This is actually called a virtual image. Of the tip of the candle. And the virtual image of this tip of the candle, it's called virtual because rays don't actually cross at that point. Rays only appear to be coming from this point. Okay, and I'm going to skip doing it for point Q. Maybe I'll put my notes up. Right, so here was point P and here was point Q. I could have another diverging packet of rays coming out of point Q on the bottom. And if I traced those rays back, then they would come to a spot here. And so I can imagine that actually there is a virtual image of the candle right here. And this virtual image has, we'll get a couple of things in here. This would be the image distance. Oh, that's not the image. This is the object. We call that DO in the formulas later. And the image distance, DI, they're the same, right? And just to begin thinking about sign conventions, when we use formulas later on in the semester or later on in this chapter, image distances for virtual images will actually be something that we call a negative image distance. So we can get ready to think about that later. And we'll also be able to say that the magnification here is 1. Okay, so magnification, which is the image distance over the object distance, is 1. Which is to say that this is the same size as that. Okay, but wait. Right, as I go like this, geez, it sure does look like my computer is getting smaller. Doesn't it look like that to you? So why did I just say that the image distance and the object distance are the same? Well, it's getting bigger as I move closer. But as I move closer, the object distance is getting smaller. Okay? So it is true that no matter what you do, right, you look into a mirror and you see a virtual image of exactly what is in front of the mirror, and it looks exactly like with the image distance equal to the object distance, and the magnification, it looks like how big it would be if it were exactly that far away to you. There's this pretty cool chapter opening question. So I'm going to show you this photo, set of 2 photos. And we're trying to figure out, well, which photo is upside down? It is really hard to tell. You can't tell just by looking at this because the water that it's photographed in is crystal clear. So it can't tell just by looking for waves in the water. We have to use some things about optics. So the answer lies in this. We're trying to figure out which photo is right side up. And it turns out that this photo over here on the right is right side up. And your book goes through it, but I wanted to go through it myself because I think that this is super cool. So if you imagine these diverging packets of light coming out of the sun, and then there's the camera over here. The camera is obviously above the water. So here's my air-water interface. I have this packet of light coming over here, and this light has to pass straight through a tree to get to there. Okay. There's another one of these rays that is going to come out and down, and then it's going to bounce off of the air surface such that angle of incidence equals the angle of reflection, and then it'll pass up to the camera. And the camera will see as though that light came from back here. Okay, so we know that this over here is the right side up image because the sun is behind the tree here and not behind the tree here, which matches what must be going on in here. Okay. Let's come back here, and I think we've already talked through this, so I'm just going to skip over that. And now let's move on to image formation from mirrors that are curved. So I've already shown this with the ray box, so I'm not going to show it again. But right, as a ray of light can come into a mirror, we can imagine there being a tangent line to this curved mirror. So the tangent line, if you remember, is this line that just barely grazes the surface so that it touches it in only one spot. Okay, a line that would not be tangent. So here would be my tangent line like that. If I drew something like that, that's clearly not a tangent line because it has to cross over the line. So when we're drawing the tangent line, we're looking for something that touches it in one spot, but it never crosses the line. So here's my tangent line, and if I draw my tangent line, then I can see that this dashed line here is the normal, and that means that the angle of incidence equals the angle of reflection. The same thing with different mirrors. This is good words to commit to memory. Concave, caves in. That's how I remember the difference between concave and convex. Okay, so this is a concave mirror because it caves in. This is a convex mirror because it vexes out. That one doesn't work as well. But if you remember the concave mirror, that can work. Okay, so spherical mirrors are, here's a spherical mirror, right? I have, it looks like this, right? It's like a little bowl, but it's a mirror on the inside. And they make images. And here's what they do to those images. So if you have rays that enter a mirror, coming in parallel to the mirror surface, they will all bend and they all pass through this special spot here, which we call the focal point. Okay? This focal point is halfway between the center of the circle and the mirror itself. So by the center of the circle, what I mean is that you can see that this looks like a spherical mirror. If I imagined kind of tracing out this whole circle, then I would have the center of the circle be here. Okay, so for a mirror, the focal point is halfway between the center of the circle and the mirror itself. Okay, so, and F is what we use to abbreviate for the focal point. And R is the radius of the mirror. And I've been telling you all year that everything has to go in metric units. And we're going to relax that just a little bit for this. If you look at a formula, you're always fine putting it in metric units. So if you're more comfortable putting it in metric units, put it in metric units. But we're going to be working in centimeters a lot. And sometimes it's nice to not have to go between centimeters and meters and then back again. The focal point and the radius of the mirror have to be in the same units. As long as they are in the same units, this equation will work. Okay, so put them both in centimeters and it will be fine, right? If your radius is in centimeters, then you'll get a focal length in centimeters. Put them both in meters and it will be fine too. Okay, so this principle of the fact that as parallel rays come in, they're focused and they all pass through a single point is how satellite dishes work. So a satellite dish is takes incoming parallel rays and focuses them to a single spot right here. So you put a little receiver right here, and this must be the focal point of this satellite dish because that's where all the rays pass through. This is actually a mirror from a concentrating solar power plant. So what is this mirror is shaped curved like this, and the sun's rays come in, they bounce off the mirror, and they all pass through this focal point here. And actually, there's a long line of, it would usually be some kind of fluid that can hold a lot of heat. So what happens over time is that the rays come in and they land on this surface and they warm up the fluid inside of here. Once you have heat, you can turn it into other kinds of energy, such as electricity. Okay, so quantitatively, we want to get a handle on how to draw images and know exactly what they look like and how they're gonna behave. So we have three principal rays. Okay, so this is a good thing to write down, and we will return to this in the future. So we'll draw 3 or 4 rays. So we're going to draw a ray that comes in parallel to the axis. After reflection, it passes through the focal point. A ray that comes through the focal point, and after reflection, it's parallel to the axis. And a ray that is perpendicular to the mirror that reflects back on itself. And a ray through the center of the mirror reflects around the mirror's axis. So these are just words to you right now. So let's give it a go and try to do this quantitatively. I'm also going to throw some formulas at you. So this will be formulas that allow us to calculate the location of the image, the object, or the focal point. If we have 2 of the 3, then we can get the third. And also how we calculate the magnification. And now I need to be careful, and you should be careful too, and go back. When I wrote this before, I wrote magnification was DI over DO, and I missed this negative. So go and add this negative in here, because that is an important negative. Okay. So here is how the book has done the first 2 rays. Okay. So I have an object here that is sending out a light, and this light is going out equally in all directions. Right? It's going out equally in all directions, but I'm going to just pick out a few of these rays and draw them. Okay, and that's what these principal ray diagrams are for. So it's going to come out in all directions, and it's going to, so I'm going to pick this ray right here. This ray is none of the rays. Oh, so this ray is a ray that comes in, this one, through the center of the mirror, reflects around the mirror's axis. So it comes in through the center of the mirror. We can think about this line right here as being the mirror's axis. And this angle right here matches this angle right here. And then that ray is going to be traced out like that. Okay. Another thing that we are going to do is this one right here, a ray that is passing out of the object through the focal point, and then it hits the mirror. And then when it hits the mirror, it happens to come out parallel. And I'm going to throw on a third ray here, which is the ray that we just talked about, which is this first one. A ray parallel to the axis will pass out through the focal point. So this is the one that I talked about with the satellite dishes. Right, so it comes in parallel to the axis. So this is the axis, so it comes in parallel. And then it's going to hit this and bend and go out through the focal point like that. And there it goes. So now we have 3 rays. 2 lines will always cross. So I strongly recommend that you always draw 3 rays on your ray diagram. Because if you have 3 rays that all are sort of more or less in the same spot, then you can be pretty confident that you drew your ray diagram correctly. And drawing correct to scale ray diagrams is something that I'm going to expect everybody figures out how to do. There is that, and there we go. And we will say, like that. Let's do an example. Okay. So we'll analyze a concave mirror. So I have a 3 centimeter high object is located 60 centimeters from a concave mirror. And the mirror's focal length is 40 centimeters. And we want to find the position, height, and magnification of the image. So this is where your ruler needs to have lines on it. If you don't have a ruler with lines on it that measure centimeters, that's fine. Get yourself a piece of graph paper. That can work, right? Those are equally spaced. Even a piece of lined paper, like college ruled or wide ruled paper, if you fold it, right, all of those lines are equal separation of distances apart. So it doesn't matter if it's a centimeter ruler, a metric ruler, you just want something where there's there's measurable distances that are the same, right, from 5 to 6 and 6 to 7 and 7 to 8, like that. Okay, so, and the reason for that is that I'm going to draw a scale version of what's going on here. Okay, so I want to draw a concave mirror. So this is the kind of mirror that caves in on itself, like that. And it says that the mirror's focal point is 40 centimeters. This meter stick is 30 centimeters long, so I can't draw exactly what this looks like to scale. But I can say, well, geez, I need to resolve an object 60 centimeters away. So what if I made every inch be a 10 centimeters? So my scale is that 1 inch equals 10 centimeters. Okay, so the object is 60 centimeters away, and we're always gonna, before I even start drawing this, let's just draw this line through the axis of the mirror. Okay, and now I'm gonna say the object is 60 centimeters away, which means that I want to draw it as being 6 inches away. So there's 10 centimeters. There's 20 centimeters. There we go. So at the location where there is the object, I'm going to draw an object. And we tend to just, the simplest thing for an object to do is to draw an arrow, okay? And so for our ray diagram, we're going to imagine rays of light coming out of the tip of this arrow, okay? So that's my D object, is 60 centimeters away. Okay. The mirror's focal length is 40 centimeters away, so I've already drawn this. There's where the focal length is. So there's F. Okay. And now this object is emitting rays out in all directions, like that. But we aren't interested in all of the rays. We're just going to draw a few special rays to make a principal ray diagram. Okay, so we know that rays that come in parallel will pass out through the focal point. So let's draw that ray, this one right here, right? It's coming in parallel. So it's going to come in parallel to the axis. And this can be kind of sensitive to how perfectly you drew the curvature of your mirror, which is unfortunate. I tend to just, rather than relying on the curvature of my mirror to be perfect, I just kind of draw a straight line here and draw all my rays as though they go to the straight line. So it goes in parallel and it turns and it moves out to the focal point. Okay. My next ray is a ray that goes in through the focal point and then it comes out parallel. So let's do our in through F and out parallel ray. Let's do this one dashed. Okay, so there's my ray. And now I can see that actually somewhere that I can maybe just barely resolve on my piece of paper, these rays will cross. But not quite. So it's somewhere out here off the page just a little bit where these rays are going to cross. Okay, so let's figure out actually where that would be. So let's extend this. And I need another piece of paper. And this will happen to you. I'll give you some tips so that you can avoid having it go off the piece of paper in a bit. But for now, we'll just make it go off the piece of paper and be okay with that. So I want to know kind of in distance. So I'm going to extend, this goes to 60. So here's 70, 80, 90, 100, 110, and 120. Okay, so I have predicted that the location of my image will be kind of right around here, which is about 110 centimeters. Two rays will always cross, so you need to draw a third ray to know if you have done it right. I really like these first two rays. I don't like this third ray at all, so I pretty much never draw it. It's just too dependent on how well you drew the curvature of your mirror. So this one doesn't work very well, but a ray through the center reflects around the mirror's axis is one we can draw. So let's do that one. Tape my pieces of paper together. Jeez. A ray through the center, so it's going to exit the tip of the arrow and go like that. And then it's going to travel out so that this angle here looks like it matches this angle here. Another way that, excuse me, so that it looks like this angle here matches this angle here. Another way that I can know that I'm drawing this well is that right when I get to the object, this height needs to match that height. So that's sometimes easier when you're drawing that. So there's my third ray, which bent piece of paper. Looks better. Comes out through here like that. And so these don't all cross perfectly, okay? But somewhere between, there's a spot where they cross, there's a spot where they cross, and there's a spot where they cross. And that's always fine, okay? Somewhere in this range, there is an image. So let's draw what the image looks like. Right, the arrow was upright, but this spot here has now, the tip of the arrow is here. So I'm going to draw an arrow that is upside down. Okay, so this is an inverted image. Let's think about, right, it's inverted because it's upside down. What's the magnification? I can see that this arrow is smaller than that arrow. Okay, so I don't know exactly what the magnification is, but I can say that magnification is greater than 1, right? The image is larger than the object, right? That's the formula for the magnification. The image is larger than the object. And actually, I guess that's the formula for it that we'll get there. It's going to be about 2. And it's upright, or it's inverted, it's larger, so it has a magnification greater than 1, and it is also real, not virtual. Okay, this is a real image because these rays really do cross, okay? These rays don't appear to be coming from a spot behind a mirror or behind a lens far away. They are actually crossing in this spot, okay? So that's the distinguishment between a real image and a virtual image. And your eye cannot tell the difference between a virtual image and a real image, right? So if your eye is out here, right, it doesn't matter if these rays actually crossed through this spot or if they only appear to be crossing through this spot. What your eye does is it takes this diverging packet of rays that are coming from the mirror and it focuses them. So it doesn't matter if these are really crossing here or they only appear to be crossing here. So this is a real inverted larger image. But we can do, and so I expect you to be able to draw a ray diagram like this. So it's something to practice, and we will practice more in this, in sort of the lecture videos. We'll practice more in the recitation videos, and try to get everyone to a place where they're able to draw this image to scale. No, wrong way. I don't think this goes up any higher. Nope, it's as zoomed out as it will go. Okay, so let's use the formulas to figure out, to calculate what we should have known. And this is where we can do our calculations first. And if you do your calculations first, then you end up much more likely to be able to know how big to draw things and where to put things on the piece of paper. Okay, so here is my 2 formulas. So 1 over dO plus 1 over dI is 1 over F. This looks a lot like the formula for parallel circuits, resistance of a parallel circuit. So maybe some of the intuition you developed over an equation that looks like that can be applied here. So we'll say that 1 over dO plus 1 over dI equals 1 over F. So right here, the object is located 60 centimeters. So that is dO. The mirror's focal length is 40 centimeters, so that's F. Okay, so if I know dO and F, I am solving for dI. So let's solve this equation for dI. So I'm going to say that I'm going to subtract 1 over dO from both sides so that I can have 1 over dI is 1 over F minus 1 over dO. Now, if I want to solve for this number that is in the denominator, I need to take to the -1 power of both sides. So I'll take to the -1 of the left-hand side and to the -1 of the right-hand side. And let me move down here a little bit. So that 1 over a number to the -1 power is just di, is 1 over f minus 1 over dl to the -1. Now we're ready to plug in numbers. And remember, I talked about this before. All that is in this formula is distances. So I'm going to go ahead and just keep these all in centimeters. And as long as f and do go in as centimeters, then I know that di will come out as centimeters. And that's fine. Or you can convert it to meters. That's fine too. So I'll go, rather than doing 1 over, I like to use my -1 power button. So I will do 40 to the -1 minus 60 to the -1. I'm going to push enter. And now I want to take to the -1 of that whole thing. That is 120. So my image distance should be 120 centimeters away from the location. And let's go ahead and see how we did. So we got probably more like 110, not 120. And that is absolutely, completely, totally fine. I don't expect your ray diagrams to be perfect. But they should, when I am grading your ray diagrams, what I am going to look for is that your rays are drawn correctly. So I care that you have drawn something that looks like it comes in parallel and goes out through F. So don't take your out through F ray and erase it and kludge it so that it no longer goes through F, but so that your image is formed perfectly at 120 centimeters. Right? I'm looking more that your ray diagrams are drawn correctly and less that these actually cross perfectly in exactly the right spot. So we predicted 110 centimeters, we got 120 centimeters. That's great. If we had done this calculation first, which we could have done, then I would have known that I needed to resolve 120 centimeters here. And that would have informed how I drew this. Maybe I wouldn't have chosen an inch to be 10 centimeters. Maybe I would have chosen 2 centimeters is 10 centimeters or something like that. Something that would make it so that I could fit 12 of them on this piece of paper. So the image distance should be 120 centimeters. And now let's look up the formula because we want to find the position. So that's the position. We want to find the height and we want to find the magnification. So we'll go over here and that's going to come from these formulas. So the magnification M is a unitless number, right? It's a distance divided by a distance, so it's unitless. It equals 1 if dO equals di. Well, I guess it equals 1 if dO equals negative di. I'll talk about what negative distances mean in a minute when we get to 1. Or if hi equals ho, right? The height of the image equals the height of the object. And it's greater than 1 if the image is greater than the object. And it is less than 1 if the height of the image is less than the height of the object. Okay? So we're going to calculate the magnification. And we will say that magnification is negative di over do. And now I know di is 120, so it equals negative 120 centimeters divided by 60 centimeters. And that equals -2. So there's the magnification. It's -2. So this negative here tells me that the image is upside down. Okay, that's what the negative means there. So don't drop that negative. That's an important negative. The 2 here says that the image is twice as big, is twice as tall as the object. So image 2 times taller than object. All right. The last thing we need to figure out is the height. So we will Now that we know the magnification, we can figure out the height using this formula right here. So magnification is the height of the image over the height of the object. So I will solve for the height of this. And if you come up here, I know that the object itself is 3 centimeters. So that is the height of the object. And so I want to solve for the height of the image. So I'll multiply by the height of the object on both sides so that the height of the object will cancel. And that gives me that the height of the image is the magnification, which is -2, times the height of the object, which is 3. So I'll get -6 centimeters. And again, this negative just tells me that it's upside down, and it's 6 centimeters tall. All right, how do we do? So this is the fancy ray diagram that does more or less the same things that we did here. Okay, and here's my mirror. And if you look at this mirror, and this is great at-home project is to get spoons and get used to looking at them, because spoons is going to give you a lot of intuition about the types of images that are formed by concave mirrors and convex mirrors, because you happen to have both of them on your two sides of your mirror, or your spoon, excuse me. So when I look in this is a concave mirror because it caves in the middle. It's what we were just working with. And you look at this, I see an upside down image of a computer screen. So, and this is what we just predicted too, right? That the image was upside down from our ray diagram. And this will almost always be true, except for a couple of special places. So let me get my pencil, and there's my upside down image of my pencil. But as I move my pencil closer and closer and closer and closer and closer, wow. When it gets close enough, the image of the pen is no longer upside down, but now it's right side up. So it's sort of right side up, and it's getting bigger and bigger and bigger, and there it's upside down. Right side up, upside down. Right side up, upside down. So something kind of crazy is happening here as this pen transforms from being far away to being closer. And the thing that is happening is that we are going from having a real image, and this is a great thing to commit to memory, a real image formed by any lens or any single mirror will always be upside down. And a virtual image formed by any lens or any mirror will always be right side up. So we are changing between a real image where the rays really do cross and a virtual image where the rays are not actually crossing. They only appear to be crossing. They appear to be coming from a spot behind the mirror. So let's do an example with a virtual image. Okay. Here is our same concave mirror, and we're going to do some ray tracing again for this concave mirror. We're going to follow the same rules to draw 3 principal rays. But now when these rays, so here's an object, and the dividing line that was between where the pen was moving in and out was the focal point of the lens. All right, so when the pen was inside the focal point of the lens, it was right side up. And when the pen was outside the focal point of the lens, it was upside down. And so our 3 rays were the same 3 rays, but we're going to draw them a little bit differently. So we're going to draw 3 rays. A ray parallel to the axis passes back out through the focal point. So it comes in parallel like this, and it passes back out through the focal point like that. And now we have to imagine that this observer right here thinks that this ray came all the way back from here. The second ray is a ray that comes through the focal point and then it passes out parallel to the axis. So this is a little bit tricky because how do I draw a ray that comes in through F when F is behind the object? So we're going to imagine a ray for this second ray that starts at F, passes through the tip of the object, hits the mirror, and then it will come out through parallel. So our in through F and out parallel ray. It's the same rule, the same ray, but we draw it a little bit differently for this object that is inside the focal point. And now these things can trace back to here. I don't like that third ray, so we're not going to draw it that way. So let's do an example. We're not ready to do an example just yet. We're going to talk about some more mirrors. So convex mirrors are mirrors that don't look like this, right? They're not this kind of a mirror, but they're what would look like if I looked at the other side of this. So I don't have a great big convex mirror, but I do have a spoon. So I'm going to show you my spoon. And here's my spoon. And if you look at that spoon, it's a little distorted because it's not a perfectly spherical spoon, which is unfortunate, but you get the gist. That is an image of the computer that is right side up, right? Down here, the keyboard, up there, the keyboard down here, up there is the screen. And as I get closer and closer and closer, it's always right side up. I get farther and farther and farther away, it stays right side up. It's never flipping. No matter how far away I get, it's always right side up. Okay? And so using the rule that I just told you, right? Right side up images from a single mirror or lens will always be virtual. So this must be a virtual image. So somehow what we are looking at is a diverging a packet of lens rays that only appear to be coming from a spot. They aren't really coming from that spot. So a convex mirror always makes an image. So here's the rays that are coming out of this tree. They're hitting our convex mirror. The convex mirror would be this side of the mirror instead of the concave side of the mirror. They hit the convex side of the mirror and they bend. And as they bend, they appear to be coming from a spot from behind the mirror. And you see actually here that this image is smaller than the object. That will always be true. These are security mirrors in 7-Eleven, right? And you've seen them, right? Those mirrors that they're always convex. They always bulge out in the middle. And the reason that they bulge out and they are that shape is so that you can see more. Like if the image is smaller, then you can fit more objects in the mirror. So it lets the guy behind the counter know if there are people stealing in a whole bunch of different locations. So right here's a couple of images of convex mirrors. I think that guy's thinking about stealing that wrench. And this objects in mirror are closer than they appear. It is printed on every single rear view mirror in the world. And the reason is because in order to get a wider field of view, your rear view mirrors are actually a little bit concave or convex, excuse me, so that they can fit, so that the image is smaller than real life. Okay, so we've got concave mirrors and convex mirrors, and we've got some examples of what we do with them. And now I think we are ready to do some more concrete examples. I'm wrong. I think we will go on from there to talk about refraction. Okay, so refraction is this idea that light bends. And I'm actually going to end this video here, and we'll pick this up with the next one.